Nice work. Yeah, my name is Patrick Grover, and I'm a principal hydrotechnical engineer. And I work with both the surface water teams and the data science and earth observation teams. And I've been with BGC for almost 10 years. And today I'm really excited to introduce Evelyn Moorhouse, who I work with. Evelyn is a geoscientist in training who uses her master's degree in data science to work with the data science and earth observation team at BGC. And she has experience in mining, pipelines, and community sectors, where her project contributions have ranged anywhere from conducting site investigations all the way to developing machine learning models. In fact, today she's fresh out of the field after doing a field stint for a couple of weeks. And we're on the data science team. We're super excited to have her back because we definitely need her help. The past year, we worked together, mostly her, to develop deep learning techniques to develop models to forecast stream flows for rivers in British Columbia and Alberta. The modeling was done to provide flood and flow forecasts to support pipeline geohazard monitoring at hydrotechnical sites, as well as to support in-stream construction work. Evelyn is also leading a large R&D project that will take the learnings from this work and develop a generalized data-driven flood forecasting system applicable to all of Canada. And the development of this technology will allow us to provide high-quality flood and flow forecasts to clients across Canada that will help them and us make proactive decisions to protect private and public assets, as well as life safety. So with that, I will turn it over to Evelyn.
Thank you so much, Pat, for the intro. Hopefully you can hear me, and I'll just let someone speak up if you can't. Okay, I'm seeing a nod. Great. And hopefully you can see my screen. So today I'm going to be talking about a couple projects that I worked on this year with BGC that were supported partially also by our R&D funding. So before I get to the modeling, I'll just give you some project context. The first project that we worked on was based in Alberta, and the goal of this project was to produce flow forecasts at gauges throughout Alberta up to 48 hours in the future. And so most of these gauges were located in the foothills of the Rocky Mountains. So I'm showing one of the gauges here so you can kind of get a sense of the catchment size, and then also the classic hydrograph of this region with that spring, freshet, peak. And so we ran these models throughout the spring, and we saw some success and had confidence in the outputs. And so then we were approached to predict discharge in the summer for a site in British Columbia. And the difference between this project was that this site was an ungauged location. But in order to create a model for this ungauged location, we used gauges with catchments of similar size and characteristic to train and test the model. So that's what I'm showing on the right here. I'm showing gauges that we used in the train and test framework, so you can kind of see their size and where we're located, which is just north of Vancouver. Yeah. And so if you're familiar with either of these regions, you might know that there are sources of forecast data available. You have the BC River Forecast Center, the Alberta River Forecast Center, and then you even have sources like Google Flood Hub. So you might be wondering, why would we train a model from scratch if there are government-provided forecasts? Well, first of all, we were actually filling some gaps. So there were places where there wasn't forecast data available. But I think almost as important, our models are probabilistic. They're not deterministic. And so what that means is that all of these sources, like government sources, they basically give you just a value of flow that's predicted up to 48 hours in the future. But what we do is for each hour into the future, we actually produce a distribution of potential discharges that could occur. So let me walk you through an example of kind of some of the importance of this. So what we might have is on day A and day B, we could have the exact same effectively deterministic estimate of 20 meters cubed per second for the flow. But on day A, the model could be really confident based on the input variables. So it's a really tight distribution. And then when you put the threshold of, say, 40 meters cubed per second on that distribution, you get a probability of, say, only 15% chance of that, magnitude of flow occurring. But on day B, there could be a lot more uncertainty associated with the input variables for the model. And so you have a wider distribution, and then all of a sudden you get a 25% probability of passing this 40 meter cubed per second threshold. And maybe this doesn't seem like much, but there could be an operational decision that's set at, a 20% probability of passing this threshold. And that's a lot of nuance that you get that if compared to the deterministic model, where, all you see is, okay, the predicted flow is 20 meters cubed per second. The threshold is 40 meters cubed per second. I guess we're good both days. So I think that's pretty important. And so what I just talked about was how our distributions change in width. And that's based on the input variables. So now I can let you know what those variables are. And really simply, they're just the hydroclimatic conditions and the weather forecast of the upstream catchment or drainage area for the site that we're trying to predict at. And so these variables come in the form of a gridded data set. And what we do is we aggregate that grid across the watershed so that we have one value for each time step associated with each variable, because the grids come in like time steps effectively. And so we have a set of variables that are both like hindcast and nowcast variables as well as forecast. So our dark green are kind of our hindcast, nowcast variables, which are, our observed precipitation, the snow water equivalent, which is how much snow is currently in this catchment, and then our soil moisture. And then really importantly, we of course have our forecasted temperature and precipitation. And then finally, for the Alberta study where these were gauged locations, we also input our most recent observed discharge. And so all of these variables, they go into our model, which, as the talk title suggests, is a deep learning model. And it's a recurrent neural network model. And specifically, it's a long short-term memory model. And so I'm not going to get into the details of how this model works. Please feel free to Google. There's lots of great resources. But what I'll say is that, as the name suggests, this model is really powerful because it has the ability to learn both long and short-term trends. And if you think about that in terms of discharge, you have, and the variables that I'm showing, you have long-term trends like seasonal snowpack that affect the discharge of a river, but you also have these short-term events like the precipitation, such as the atmospheric river we just had here on the West Coast, or, those big thunderstorms we get in the Rocky Mountains in Alberta. And so all of this gives us our output of the distribution of discharge. And so now that we know the data and the model, I can talk a little bit about training architecture. And this is simplified, but it should hopefully give you an idea of how we actually prepared these models. So the first thing that we do is the data that we're using for training, which is often coming from a gauge, is we create a historical source of truth data set. And what's important about this data set is that all of the variables are aligned temporally with our observed flow historically. And that's important because, as I mentioned, we have both, hindcast, nowcast, and forecast variables. So the way that we shift these variables is really important to make sure that they're all, aligned properly with the observed flow that then occurs. And so once we have this kind of source of truth data set, then we can go on and train our model, which in this case is actually 48 separate models, each for the hour we're trying to predict into the future, like from 1 to 48. And I'll explain how we do this by kind of walking through the 1 hour example. So basically what we do is we just shift the observed flow by the amount of time that we're trying to predict into the future. So in this case, 1 hour. And this is important because what's happening is the model is saying, okay, at May 11th on 12 p.m., this is kind of what's currently going on in the basin in terms of moisture. And then this is our forecast. And then we see, okay, this is the flow that happens an hour later. And it starts to build that relationship with, okay, current conditions, flow an hour later, let's learn these trends. And so we do this all the way up to 48 hours into the future. So shifting, that observed flow by 48 time steps. And so what I will say is that I think in terms of this entire process, this is the area where there's the most room for improvement. I think and what we'd like is that we have a single model that predicts all 48 hours into the future, and we have kind of the relationship between each prediction incorporated. But this was a really straightforward approach for us to get our end goal of, this 48-hour window of prediction. But what I will say, and what made us have faith in this approach, is that what we saw is that in the 48-hour model, the features with the most importance, or variables with the most importance, were our forecast variables. Whereas, of course, in our shorter term models, like the 1 hour, 2 hour models, the most important variables were just the past flow. And so that gave us confidence that the models were picking up the proper trends based on how far in the future they were trying to predict. And so the final thing that I want to talk about in terms of actually training the model is how we got a probabilistic output. So the model is just trained using TensorFlow, a Python package, but TensorFlow has an add-on called TensorFlow Probability, which allows you to change the output of a neural network to be parameters to a distribution rather than a single, deterministic best guess point estimate. And so since we wanted to predict probabilities, we wanted to output a normal distribution because that's a very simple way to do that. But if you know hydrology, you probably know that flow or discharge doesn't follow a normal distribution. It follows, at least in BC and Alberta, a log normal distribution. So to get this, normal distribution output, all we did was we took the log of the flow data and trained the model on log flows. Then after the model output, the parameters to the distribution, we could then just convert back to, our classic discharge in meters cubed per second. So hopefully you understand a bit about the model itself, but now I can dive into performance. So what I want to just highlight in terms of model performance is that to actually kind of evaluate our determinist or our probabilistic model, we need to distill it down to a deterministic model to kind of get these performance metrics. And so that's basically what I'm showing in these right three plots here. So these are three of the gauges in the Alberta study. And I plotted 4 of the models, each 12 hours apart. And what I'm plotting is the median of each of these models for each of these time steps. And so that's basically our best guess, or as close as we could get to our deterministic estimate from these models. And I'm plotting that against the observed flow. And so from these time series, I can also derive a Nash-Sutcliffe efficiency score, which is the standard in hydrology, but it's actually the exact same formula as an R-squared score. So if that's a metric you're more familiar with, you can think of it in terms of that framework. And so really quickly, what we see is that larger catchments performed better, which makes sense. They have a longer response time compared to smaller catchments, which are flashier. And then obviously shorter term forecasts did better than the longer term forecasts. But something that became apparent through the plots that you don't really see in the Nash-Sutcliffe efficiency scores is that there's a lot of false peaks. And these false peaks would be pulling our Nash-Sutcliffe efficiency scores down. But what's kind of reassuring is that what we see is that these false peaks are almost always tied to a forecasted precipitation event. And so that's really good because we have an explanation for these false peaks. But the downside to that is it means that we're really dependent on the accuracy of our forecasts. And so that's something that we really have to keep in mind, as we're interpreting these model results. And so now I kind of want to bring it back to our probabilistic framework and kind of evaluate these models in a probabilistic lens. And I'm going to do that by focusing on the top gauge, which ends in 13. So I'm just going to call this gauge 13 going forward. And if you look, you'll probably see that all of the medians of the models basically didn't predict the magnitude of the actual annual peak at this gauge. But if I plot the 95th percentile of all of these models, you'll see that we actually basically captured the magnitude of that flow. And so it means that, yes, we didn't assign a very high probability of that flow occurring, but the models did say this flow is within the realm of possibility. And this became important because as we were running the models in the spring, if we had the 95th percentile actually hit one of the thresholds, it would make us take pause because that didn't happen very often. And so what that means is all of a sudden, oh, there's a chance that this threshold could occur. So do we need to take any action? And so kind of keeping in mind with this 95th percentile that I'm talking about and the difference in distribution, I'm just going to walk through one more example. And it's with this same gauge, gauge 13. And this was when we were actually just testing these models this year, running them for the first time. And so what I want you to focus on is just this bottom slide. I'm showing the 95th percentile as a dashed blue line. And then we have our median, which is the dark blue line, which stays pretty much steady this exact 2 weeks, or the whole 2 weeks. But if you notice, around April 3rd and 4th, when we have that peak in, the 95th percentile, it's corresponding to the input variables, which I'm showing on the top graph, but I'll just walk you through right now. So basically what we have is we have a couple days of really warm weather, and that means that our snowpack decreases. So that's adding water to the system. And then we also have a bunch of forecasted precipitation that's occurring in those days with temperatures above zero, which means rain. So the model sees all of this and says, okay, there's a lot of different ways this could play out. So I'm going to give you a wide range of possible flow values. But then we fast forward a few days and temperature drops back below zero and stays consistently negative. And then our distribution tightens right up, almost too tight. We almost missed the observed flow, but it tightens right up because it's really confident, because it says temperatures are negative, precipitation is going to be snow. I don't think any big flood events are going to happen. I'm quite confident in this, this range of values. So I hope through these examples, you can see the value that a probabilistic model adds to kind of these predictions of flow. And that we actually were, able to run these two models on projects, or these different types of models on projects in 2024 and help clients make decisions. And so what Pat alluded to and what we're really excited about is that, we have this active R&D project where we really want to standardize and improve these models. There's I have so many thoughts. I could go on and on, but I think it's really exciting, and we kind of want to make this, a system that we can apply across Canada at both gauged and ungauged locations. So that's all I have time for today. That's the best email to reach me at. Thank you so much. And feel free to ask questions, and I'll try to pop in the chat too to see if there's any there.
That's great, Evelyn. Thank you very much. Yeah, that was a great presentation. We've got one question. I'll read it out here. Is the model trained on observed or historical data and then applied to forecasted variables to predict the future distribution of discharge? Also, why did you specifically mention forecasted temperature in your explanation? Shouldn't other variables like precipitation be also included? So, yeah.
Okay, I'll try to dig in because there's a lot there. So the model is trained on, and this is just thinking of wording this properly. So we have historical forecasts, and we also have historical observed data. And that's really at the core what the model is trained on. So we can train on, from May 1st, 2022, we have what is the precipitation at this hour? And then what was the forecast 48 hours from then? And so that's kind of the core of the model, is that we're training it on both, historical forecasts and then historical observed data. And in terms of, I think, the temperature part of the question that you asked, we also include forecasted precipitation. So we're training basically our two core forecast variables that we can kind of align up to correspond to what happened historically in flow. We have forecasted temperature and we have forecasted precipitation. And then we take in what the past temperature, what the observed precipitation has been, and then kind of soil moisture and snowpack. So I hope that helped a little bit with the question. There was a few parts.
Great. I think we have just one more minute here. I got another question. How is this connected to probabilistic models with climate change models, i.e. RCP 8.5? So I think it's a question about whether or not this could be used for climate change analysis.
Oh,
It's in the chat. Sorry. Yes, it's in the chat.
Yeah. I think what's really critical about these models is that we're working with present time smaller scale data sets. Our resolution is hourly, and with those climate change data sets, they're longer term durations. They're more kind of annual based, at least in my experience. But I think you could very much apply a super similar framework with that data set. You just kind of shift that temporal resolution. But we haven't done any of that work yet, just to kind of address that question.
That's great. Well, thank you, everyone. Thank you, Evelyn, and thank you, everyone who asked questions there. And now I'm excited to hand it over to our next presentation, which will be introduced by Lauren Hutchison. Thank you.
Yeah, thanks so much, Pat, and thanks so much, Evelyn. Those are pretty tricky concepts to get through, and you did a beautiful job of walking us through what a long short-term memory model is.